recording of like pre-recorded lecture of today's topic you haven't uploaded?
Oh, I have not given that. Yeah, I'll give that. Don't worry.
Okay.
I'll give all that. Yeah. I have it till scattering. Everything is very nicely pre-recorded. So are the pre-recorded ones useful? I think they are more useful than the class.
Yeah.
It's everything is done extremely in a detailed way, which is impossible to do in class like that. So although the pandemic was overall bad, of course, but there are some good things. It's like when a flood happens, a lot of destruction of property happens, right? But when the flood leaves, then the floodplain becomes fertile. So it is like that. So when the pandemic left, it left us with some new things, some new topics. I wouldn't have thought about doing pre-recordeds without the pandemic. Anyways, so today we'll start these variational methods in quantum mechanics. And this topic is actually very deep. It's a very big topic, and quite a large amount of modern research is what happened. What did you try to do? Yeah, can you leave it as it is? I will not experiment now. Yeah. So a large amount of modern research is all about, I mean, it's centered around these variational methods. And the reason is a large number of, so I'll explain you in a moment the reason. A large amount of problems cannot be done perturbatively. They are non-perturbative problems. But we will not be able to do true justice to this topic because of this course has to be, it doesn't emphasize on this much. So I will just brush over some basic, very simple idea, and then if someone is interested, they can go over it. Yeah. So first point to notice that it is a useful, very good tool to understand properties of ground states. For ground state, for excited states, not so much. That doesn't mean you cannot do it at all, but for excited states it's much more difficult and not very meaningful. And there are again a lot of research is going on, like in the context of MBL and all, where people are trying to understand, where for most physical problem, understanding the ground state is the main thing. Once you are even you are working in a high temperature environment, you can show effectively the ground state is basically the most important, and everything is happening at ground state or around ground state. But that is not true for certain modern problems. So then you need to know the full spectrum or some middle of the spectra or excited state. Then these variational methods is very difficult, and it's an ongoing work, and people are trying to develop these for this excited state, etc. But for mostly the form of variational principle we will do, it's not useful there. Now you have basic idea about variational methods, right? You studied in classical mechanics and math methods, right?
Yes.
Extremization of action,
Yes,
right?
sir. Yes, sir.
Calculating geodesic and all that. Okay. So the main point is it is applicable for system that doesn't have a small parameter. There is no epsilon. There is no epsilon. And then we have to, and there is no way to formulate the problem in a way that as if that such that there is an epsilon. And it is not exactly solvable either. So it's not like you are writing it some H0 where you know the solution and it is not solvable even. Okay. So this is usually the class of problem of some physical examples are this example of fractional quantum Hall effect. So this I am particularly taking this example because this is an example of the best, most complicated problem for which we know a very good variational solution. And Laughlin won a Nobel Prize in '98 for this variational solution. and it is it was 99.99% correct, like accurate from what is known from other ways. And we will also discuss that how do you know how correct it is if you cannot even solve it. Whatever you got, how will you know that? So it turns out to be one of the most successful. There are some other, what we'll do in the class is some smaller example like particle in a box and hydrogen atom, helium atom kind of problem. We will not go, of course, in this detailed problem of fractional quantum Hall effect. It is fractional quantum Hall effect is basically a problem where electrons are confined in a 2D plane, strictly confined in a 2D plane, and they are interacting with each other via Coulomb force, and there is a strong magnetic field. And the magnetic field is very strong, such that you have to take into account the interactions, and the potential term because of the motion is stronger than the kinetic term. And you cannot treat at all the electron as a free gas, you have to treat it like a liquid, correlated liquid. We will not go to that kind of complicated problem, we will go do some simpler problem. And the references is mostly Griffiths, a little bit of Sakurai and Shankar. Shankar has some discussion on excited state variational method. Other books only have it for ground state. Okay, now let's talk about setting up the problem. So the success of this method depends a lot on setting up the problem, which means how you start, how you give the initial answers. So you want to solve a problem of this form. And we know that in perturbation theory, so let's say, let me write it down as ground state. So we know that ground state has the lowest eigenvalue. And all other state this is just a generic structure of a problem. And let's say we somehow cannot solve 0 or n exactly. Notice that this could be sometimes a requirement even for perturbation theory. In perturbation theory, assumption is you know the H0 part, and then you want to calculate the full H plus H0 plus H1. But there is no guarantee that you won't even know the H0. So that is the point. And when that happens, how to do that? How to handle that? So we want to guess a 0. As I said, we are going to do ground state, and we are trying to do it from various knowledge of the problem or physical intuition. So this is one thing I want to also emphasize. This variational approach to quantum mechanics or variational method of solving is more art than science, which means there is, you will see there is a very physical, there is a very clean formalism in perturbation theory. It's basically you plug and play. If there are formulas, you use that, you put this, you get this result, first order, second order, very controlled, very systematic. Here you have to somehow guess this using whatever you know about the problem and some physical intuition. And as I said, it's not so easy, and that's why people get Nobel Prize for doing it. Okay? It's not a very systematic, it's not the problem that anyone can solve it once the problem is formulated. Of course, formulation is also difficult, but that is the case for perturbation theory. So we want to have this, and we call it the Ansatz or trial. Ansatz is a German word, Ansatz or trial solution, and you want to see how good is the trial solution. Now you might ask, how do we know how good it is? Because you have nothing to compare against. We don't have an exact solution for an unknown problem. So one way to do that is either you know it somehow, like from experiments or something, or you see if you are estimating the ground state. So whatever you guess, it cannot be higher than the ground state, right? Then that guess is, it cannot be lower than the ground state. So you have to see if you are approaching lower and lower and approaching the ground state. So you'll see this in a method. So as you get your transage gets better, If you have multiple answers, how do you know which one is better? Okay? That is the big question. If you have nothing to compare against, and let's say you don't even have experiment, then what to do? Okay? So then simply you will see that which one of these two is giving you lower energy, because you are estimating ground state. If one is lower than the other one cannot be the correct answer, right? It should be that simple, but turns out it is even not that simple. So there is a very strong debate in the field I work on, that it's called quantum spin liquid. So there is a material called kagome. Not material means a lattice called kagome, and there are two unsaturated ground states, Z2 and U1. So every other year, other groups write papers, say no, U1 is ground, and another state said no, Z2 is ground state, and they debate over that, and many years it is going on. There is no solution yet. So this is very fuzzy and difficult. If there is an experiment that can settle the debate, because U1 and Z2 has a fundamental difference in characteristic, and some experiment supports U1 in certain systems. Okay, let's come back to the point. So now I have a ground state which is not the correct ground state, of course, because we don't know the correct ground state. That means it should be expressible in terms of the current ground state. Correct states, all the states, it should be expressible with this coefficient, and this is your Cn n. And for a very good answer, a very correct answer, we know that C0 will be 1 and Cn will be 0 for all n not equal to 0, and sum over Cn square must be equal to 1. So this must be true for a very good answer, because that means you have exactly got the ground state. But a quality of answers could be determined by saying how small are the Cn, if you can express them in terms of the X. But it is, again, as I said, it's not always easy to guess that. So let's try to see what more can we say about this problem from these answers. So let's try to calculate this expectation value.
Sir, camera.
Yeah. So the expectation value of ground state energy should be C0 square E0 plus En, and this must be greater than C0 square E0 plus right, and this is nothing but E0, because this total sum is 1. Okay, so that proves that this guy is always greater than E0, which means whatever is your estimate, that can be minimum the E0, because the minimum is the ground state, which is the lowest energy state, and whatever else you do will overestimate the ground state energy. So a good check to quality is that if you have multiple of them, which one is the lowest? So that is most likely to be close to the correct answer, right? So now let's try to do it systematically. So first of all, it seems right now there is no systematic way to do it. It is just either you have it or you don't have it, or you just have multiple O tilde and or 0 tilde. And how do I systematically improve that? Can there be a parameter? So let's say there is a parameter to this ground state. I'll give you an example immediately afterwards that what are those parameters. Let's say there are some parameters for these ground states. So this could be, for example, if the ground state of this form e to the power minus r by d, or if it is this hydrogen atom type ground state, if it is Gaussian, so r square by s square, then these a and d are the parameters. So that's what I mean by parameter. Yeah. What's the question?
Yes, sir. Can you repeat that conclusion again to that minimize that ground state 0 H0? That
Yeah.
that's
So
what.
you understood this point, right? That your unsaturated ground state will always overestimate the ground state energy, right? It will always
Yes.
be higher than the actual ground state energy.
Yes.
So that is the conclusion from here. So this is what I proved, and
Okay,
that
we are
means if you
trying
have
to get
multiple
that.
answers, so that means if you have multiple answers, then the better answer is the one which has lowest energy. Right?
Okay, got this.
So that is the way to see that if you have multiple guesses. Now here I am trying to say if you have given a guess, okay, so it is like either it's like you shoot the solution, you either hit it or miss it. That's what it seems like. But if you are given, that was not the case for perturbation theory. You could improve the solution by going higher and higher order. So now let's say you want to improve the solution. Is there a way to do it? It turns out there is a way to do it, but that is not that doesn't solve the entire problem, but it solves some problem. So let's see what is that way. That way is, let's say I have some parameter in a given family of solution. There is actually one way to go beyond that, but that will not do in the syllabus. So let's say I have one family of solution which has some parameter, and by parameter I mean this kind of things. And we can calculate the expectation value.
Sir, how they get to know that different kind of parameters which will support this lowerizing that E naught? Means they tried to
Sorry,
solve
say that
this.
again. What are you saying?
Means how they decide that parameters. Means how they get to know these parameters will give more accurate solutions. How they get to know?
No, what do you mean by how they know? So this is a function,
Means
let's say, with some
yes.
normalization.
Hmm.
So what should be the parameter here? How
So
many choices do you have?
okay,
There is only one choice, right? There is
one
only one
choice.
parameter,
Yeah. Hmm.
right?
Yes.
Okay, so now my prescription is to look for solution that does the following. That minimizes the energy, which means I have to find the derivative. Okay. But still there is one catch. It still tells you it is within a one family of solution which has a parameter. It still matters that how good your initial guess, how you choose that family. So let's see an example. So ground state, so this is hydrogen atom. So the ground state is,
Sir,
yes.
how the guesses are made, like how when I see a problem, how to guess the wave
That is what I'll
function.
do. That is
Okay,
what
okay.
I'll do. It's physical intuition. You look at the problem, you stare at the problem, and try to figure out. Okay?
Yeah, but
And I'll do.
if
There is
any
no systematic way. That is the point, and that's what I'm saying. It's an art. It's not science.
yeah, yeah, but
There is no
sometimes
formula.
yeah, but it may happen that we do not have a clear picture of the potential. So in that case,
You don't have what? You do not have what?
the
Sorry.
clear picture of the potential under which the particle is moving. So in
Yeah.
that
If you don't even know the problem, then how will you even think of a solution?
no, I am saying that like in the I the liquid drop model or those models for nucleus. I am forgetting the name.
What model? Say that again.
Liquid drop model or the structure for the
Yes.
potential of nucleus. I am forgetting
No, the
the
potential is clear, but it's an approximate potential, right?
yeah.
It's a physical picture which you develop to phenomenological.
Yeah.
Understand what's the scope of the chapter? As I told earlier, wrong problem, wrong solution. It's the domain, right?
Okay. Okay.
Problem. Now they
Sir,
are asking what is
I
the solution.
couldn't hear you. There was a lot of like your voice.
Yes. Sir, your voice is breaking.
Can anybody else hear me?
Yes, sir, same here.
Okay. Now can you hear me?
No, sir.
It's still
The board is blurred.
Sir, sorry.
Okay. So we have to see what is the scope of the problem. The scope of the problem is when the problem is well defined, how do you find a solution? That is the scope of the problem. Now, of course, the problem is also a long problem. How close you are to an actual picture, right? Tight binding model of Alid or all these liquid dop model, they are all approximate picture of a physical scenario. Okay,
Okay.
make sense?
So in those cases, I have to like take the approximate picture and using this
That is almost
method.
always true. All the problem are like that. There
Yeah.
is no perfect circle in universe, right?
Yeah.
The only perfect circle is the one that human draw. Even anything you do, like you draw elliptical orbit, a circular orbit, or they are all approximate picture, right? So the question is, given the problem, how you solve? That is the method. That is what we are discussing. Now,
Okay.
how will you model the problem? That is not so trivial. That requires a lot of physical intuition as well. And this is almost always in the way you learn is very different. Many times you know the wave function, but you don't know the Hamiltonian. Like we are writing down the Hamiltonian as if we know the Hamiltonian. There are problems where you know the wave function, you can measure it, you can guess it by various ways, but then you don't know what whose solution is that. So then you have to guess the Hamiltonian whose solution is that wave function. So these are it's very non-linear how actual work is done.
Yes.
So this is why also like it's important that you have a strong command on this on the technicalities and the tools. Then only you have some hope to work on the space which is where things are fuzzy. It is like music, right? You learn the rules, but when you play, actually it's all improvisation. There is no rule. So it's like that. Well, there is some rule, some grammar, but it's a lot of fudge factor is there. So now you will probably find it shocking. Okay, you don't even know the Hamiltonian. You don't know. I mean, who told you that Hamiltonian is this? Nobody knows. It's a good enough grace. And that's where comes experiment and other things. You make a prediction, you see if it fits with the experiment, then it is good enough for this purpose. That's how you develop the subject. So we know this is the ground state. J square e to the power 4m by 2h cut square. N equal to 1, ground state. Okay. And suppose we don't know this. We don't know this. So we want to guess this. So let's say we guess this e to the power minus r by d. We guess it will be some exponent, some strongly decaying form. Now we could have guessed it also this. We could have guessed it also this. Some strongly decaying form. And let's see how close we get, how good we get with that. So let's start with this and normalize it. So if you normalize, this is what it becomes. And then you calculate this expectation value. Which is basically so this will there are two terms. First term is this kinetic term. So kinetic term will be, let me write it here because it's a lengthy expression, pi d cube 4 pi r squared dr e to the power minus r by d d2r dr2 plus 2 by r ddr e to the power minus r by d. So this will be the kinetic term if you expand it fully. And the spherical harmonics part will give you just the constant 4 pi because there is no r dependence here directly. And then this will give you the potential term will be 1 by pi d cube minus j d square. You don't need to copy it, it's there, I'll give you the notes. But it's useful to copy, otherwise you feel sleepy. Okay, so this is the full expression. Do some algebra. I am not doing all the steps. When the dust settles, you get this for the kinetic term and this for the potential term. One is h cut square by 2m d square, another is minus j d square by d. So what's the next step? According to this formula, according to this, you have to take the e as a function of d. D is your parameter. So this is, you got h square by twice m d square minus j d square by d. So you have to take a derivative and set it to 0, then you know the right d. So that will give you So the correct result according to the variational principle, the result is e cube by pi h cube zm to the power 3 by 2 e to the power minus r zm square by h cut square. Okay. Now you can play the same game with this answer. Okay. I am not doing the calculation. I will just write down the what you get if you do that calculation. So in this way, you can imagine the psi naught you got it's same as this psi naught. Okay. So you will get the correct E. You will get the correct E. But if you take the Gaussian, it turns out what you will get, the E minimum, you get 0.85 E, which is you make a 15% error. Okay. So just to tell you that the Gaussian was a bad guess, but there is no way to guess that, so you will get it like that. But also notice that if you do the Gaussian, the E minimum you get is 15%, in the sense that you get this to be minus 4 by 3 pi z square e to the power 4 by h square m. So it is this number, and that will tell you that you are like, if you compare it with the actual E naught, you will get this is 15%. Okay. Any confusion about what we discussed so far? Can you do the Gaussian calculation based on what I have shown in the exponential form?
Sir, here we have the ground actual wave function and the energies to compare to in the hydrogen atom.
Yes.
So we know, but and we can we take this as an answer for a higher atoms like helium, lithium, and just try to change the parameter and try to get the what is a ground state wave function in the same way.
Yeah. So you are saying how will you know that this is better? Okay.
The same like because this.
So
Like
can you use so it's a good question. So can you use a physical argument that will tell you that why you should start with exponential and not Gaussian? Can you think of a physical argument or a mathematical argument? That's the question, right?
Yes, sir.
Okay, can you? I think you know the answer. It's already discussed in quantum 1. Let me give a hint. So think of the asymptotic solution of the Coulomb equation or the Coulomb potential. Uh, the Schrodinger equation with Coulomb potential. Can you think of the asymptotic solution? Anything you remember from your past life in last semester? Okay. So the asymptotic solution, so this is a good point, tells you that why you should start with. So that's what I'm saying. This is a place that why you are thinking even of a decaying solution, and a decaying solution in exponential form, not a Gaussian form. So for that you have to look at the remember in the asymptotic solution for the bound state, you get rid of all the 1 by r type term and you are left with okay, and the solution for this is okay. Now are you following?
Yes, sir.
So you look at the asymptote and guess the form. Okay? You know you want to smoothly connect the solution with the infinity r going to infinity limit, the bound state solution. So that is why we started with the exponential form to begin with. The Gaussian is actually not that bad. We did the Gaussian and it was not so bad. It was 15%. And you will see in a moment that when people initially tried to guess these various energy levels, and it is actually very fascinating that when people tried to guess these various energy levels and they found the solutions which were like 200% off, 50% off, and then they improved something a little bit and it suddenly became 5%, and then, because suddenly you are very close to the solution and you don't even know when you are close. So then you increase a little bit, it become 1%, and a little bit it became 0.1%. So that kind of so you know you are heading in the right direction because gradually getting better and better. So let's see some example of this sort. We'll see some example. Okay. So you look at the information, all the information you know about the problem, and try to come up with an answer. That is the thing. So in this case, that information was the asymptotic form. Okay, so let's now
Sir,
talk about another problem, particle in a box. Yeah.
sir, sir, will like how does some in this variation principle problem? How does increasing the number of parameters which we take the for varying helps in improving the solution? Like if we take instead of 2 parameters, if we
You can
take three.
increase the number of parameter, but there is a question of, as I said, there is this is more an art. So you can there is a very famous statement by, who is that guy, von Neumann. It says with 4 parameters I can fit an elephant, and with 5 parameters I can make it wiggle its trunk. And somebody actually tried it. You can actually do that. You can if you have 4 parameters, you can draw a curve like that. So you can literally draw an elephant. Okay, you can you can tweak the parameters and becomes an elephant, and with 5th parameter you can move this trunk up or down. Okay, so the point is you can always increase the number of parameters, and with as you know, so if I give you a data set, right? I give you some data set, okay, and I ask you to fit it with one parameter. So this is your data set, something. So you can do something like this, right? And you can use an arbitrary order polynomial with n parameters. Then you can fit anything, right? You can fit any complicated curve. But that's not a good theory. You want a good theory means it has to have minimal number of parameters. So it's a question of aesthetics and question of accuracy. So if a theory has too many parameters, this is often a point of criticism actually. If a theory has too many parameters and unnecessary parameters, even if necessary, if there are many parameters, the solution is not reliable. Okay? Make sense what I'm saying, or it's fuzzy to you?
Yes, yes, it makes sense. Like what
So
those
you can,
unwanted.
first of all, you have to justify in this problem, this particular problem, you cannot even justify a second parameter. Okay, you can always say, okay, what about this? I can do this, e to the power minus r by a, and then we do some r minus b by a, something of this sort, right? So where else you can put a parameter? Yeah, two parameter. But this second
So,
parameter physically is just shifting the origin, doing nothing else. And even if in a complicated theory, you can add many parameters by somehow to construct a peculiar ansatz that may not be physically meaningful, because one can always say with many parameters you can fit anything, right? That doesn't give you any physical insight. Yeah, what are you saying?
sir, even this Z could also be taken as a parameter, right? Or since it's an hydrogen atom, this Z is taken to be one. That's why we are
Yeah,
not
in
taking
hydrogen atom Z is 1, right? Why will I take the Z as a parameter? We are talking
this.
about hydrogen atom. Have you taken a course on variational principle before?
Yes, sir, it has been taught in
Yeah.
quantum chemistry
So
too, and quantum chemistry one also.
okay, so you probably know this chapter. Okay, so yeah, so you probably know everything I'm saying. So don't skip ahead and say what I'm going to say next. Okay, so Z will be a parameter for a defined problem. This parameter problem you cannot, right? You are arbitrarily putting Z as a parameter. Z is not flexible in this problem. So you have to think physically about the problem and what are the available parameters. Okay. Now this is because you said that it is interesting. So I worked on a research problem which had 48 parameters. If you do a problem with a 48 parameter, people will immediately trash your paper. So then we use symmetry arguments to reduce those 48 parameters to 2 parameters, and it was extremely tedious work. You look at the point group symmetry, apply the full power of group theory to a very complex problem, use all kind of symmetry arguments and break down 48 to 2 parameters which are independent. You can show that other parameters are related by symmetry. So then it's a beautiful theory. Then you have a 2 parameter theory that might have some physical meaning. Otherwise, if you start doing a 48 parameter theory, anything you can fit anything. Okay. So that's why there is this theory of grand unified theory, and all people are trying, which is 100 parameters, or they are not good theories. They are just fitting, curve fitting. So here we are doing something a little more than optimization and curve fitting. We're trying to gauge the actual physical wave function. Okay. So now I'll do a particle in a box problem. Shafi, you know this problem, particle in a box?
Using variation principle, right?
Yes.
Yes, sir.
You did this chapter, right?
Yes, sir. All these
Okay.
examples were done.
Okay. So help me.
Sir, the board. Yes.
Okay. So particle in a box problem is this. Okay. And what do you know about the problem? It is 1 by, so let's say minus a to plus a, so 1 by root a sine n pi. So I'm trying to guess the ground state, so n is equal to 1. And E naught is okay. Now let's say I want to guess. So this is what I know already, right? But let's say I don't know this. So how will I guess it? Someone
Sir,
else? Yeah.
the wave function will be sine or cos.
Oh, a
Means
function
it
is
is
cos, right?
symmetric.
Okay, let me fix
You
it
are
just a minute.
guessing that ground state. So
Wait. So if x is a, then it is pi by 2, and sine pi by 2 is what?
No,
1,
he's
right?
saying that when the particle, I mean the box is minus a to plus a, then the ground state starts with cos. I mean the
Oh, I'm
ground,
just trying to guess why it is consistent with it. So if I write it cos,
yeah. Then the ground state has to be even, or there
right,
will be no
right.
node.
Because if my x is a, this has to vanish, right?
Yeah.
And it is not vanishing here.
No, sir,
Good.
the length is 2.
Okay.
Also,
Yes.
there
Okay.
should be no
Or
node.
we can write less 2n plus 1 pi by 2, that kind of
Yeah, we can
sign.
also write to an
Yeah.
odd number. Yeah, that is fine. So the point is, I want to guess this wave function. So other than Safi, others. So what are the important ingredients? How can I guess this? Let's say I don't know this. What I know about the problem?
Okay.
So vibration of string.
Yeah, sorry, say that.
Standing vibration of string. That is the standing wave.
Sorry, say that.
The box length.
Yeah, I can't hear clearly. Can you say it?
The standing
What?
wave solution.
Standing wave. Okay.
The box length is known.
Box.
The potential box length.
Potential is known.
Yeah, potential is known, of course. It's particle in a box, right? I am saying I don't know the ground state and I want to guess it. So what are the physical inputs I have? Okay,
The
Safi,
box
you can.
length.
For only kinetic energy.
Safi, you know this, so why don't you tell?
So one is the a value of a, whatever is like we can consider this as a standing way, like since
Why are you going all in standing wave? So think much more simply that what is this solution? What are the important things happening in this problem? What do you know about the ground
The
state?
box length is given. That is the physical thing I
Yes,
can know
that
from
is fine.
outside as previous.
What can you sketch the solution?
So, by using knot theory.
Yes.
sir it should like we know that it should
Node theory.
vanish at minus at the endpoints, and in between it could
Okay.
be any arbitrary curves. Like we can take a Gaussian also as a ground state.
Okay, so it should satisfy node theorem. Okay. So
Yeah, node theorem.
Gaussian you cannot take. Can you take Gaussian?
No, sir.
You have to put it 0, right? You have to make it exactly 0. So you know this, it is 0 here, and it is not crossing line anywhere in the middle, right? So these are the three information you know. So let's draw something like this. Okay? And you do node theorem and boundary condition tells you this much. Okay? Now we want to say a
And
little more. What?
only kinetic energy will be there when the
What do you mean by kinetic energy?
means
Means the energy
the
contribution is only kinetic part of the problem.
I am not following. What are you saying?
He's
means when
saying
the
that the
particle is
energy.
inside the box, the energy of that particle or that wave function is wholly kinetic. Means we can, if we can
Yeah,
use
because the
that.
potential comes as a boundary form. So this much you know about the potential, right? So let's do a guess. So of course, cos is a good guess, but we are pretending we don't know the cos, right? So let's guess it with a parabola. So let's call this. Right? This is a consistent equation of the wave function with the picture. So let's see how good it is. There is no variational parameter, by the way. Notice in this way of writing. So let's guess the h. So I'm not saying this is the best answer. I'm just showing this is a consistent answer, because I'm pretending I don't know the solution and I'm trying to figure it out. you can come up with something which is similar. It has to have this even structure and other things which we have pointed out. Right? So if you do this integral, you will get 10 by pi square h cut square 8 square m. So you will get 1.0132 E naught, which is basically 1.3% close to accurate. Okay. So we started with quite bad guess, like it's parabola or it's a cosine. Of course, if you expand cosine, you get a parabolic form. But this parabolic form gives you 1.3% close to the actual answer. And it is of course higher than the E naught, because as we said, it's not, whatever it is, it's not the correct ground state. So now let's give it a parameter. So right now there is no parameter. So let's say I will say, no, it's not exactly parabola, but almost parabola. So I can give a parameter. I'm trying to improve over this answer and see how good we can get. So then I write down the h bar. So do a little bit of this calculation and show that the h bar will be okay. So what we have to do? We have to do del h del lambda. And if you solve this, you will find the lambda is 1 plus root 6 by 2, which is 1.72. So it's not 2, parabola is 2. This is a little less than 2. So if you now plug it in, so now if you plug it back, you can estimate the h minima to be 1.00298 E0. So it is like, so it becomes 0.3% accurate as soon as you introduce a parameter. Okay. You are following what I'm doing?
Yes, sir.
Okay. So now I want to ask another question. How accurate is it to the ground state? So for that, so notice that if I have given you these two solutions, right? If I have given you these two solutions without knowing anything about the original solution, you could have said that this is better simply by the fact this energy is lower than that energy. So if between these two solutions, if you have to go with one, you must go with the one which is lower energy. That means it's closer to the actual ground state. So this is the kind of debate this U1 versus Z2 people do. They say, look, my state is lower. No. Someone said, no, look, mine is better. It's a little lower, and that sort of debate goes on. Okay. So now I want to calculate another quantity, which is how good is this? I want to estimate this. So how well it is projected along the actual ground state. So this can be actually, so you at a priori you might think, oh, how will I even know that? Because this quantity is an unknown quantity. I don't know the zero. Then how can I even estimate that? So it turns out you can estimate this with very simple identities. So we want to calculate the h minima, the expectation value, and that is nothing but k equal to 0 to infinity k0 mod square ek. So this is the definition of that, and this must be greater than 0 mod square E naught plus. So I'm writing the next excitation. So that is 9 E0. So the lowest one is E0. So next one is what? 4E0. Third one is 9E0. So I'm rewriting it in terms of that. Okay. Because this is all the states, this is just 2 states. So this will be now you can plug in all the numbers and you get this to be, because H mean is basically 1.002980. So the E, it doesn't matter that you don't know the E0, it gets away. So you get 0.99963. Okay. So that tells you, that is pretty satisfactory. It tells you the overlap between the actual ground state and this ground state is 0.99963. Okay. So that how far it is from unity, from 1, that tells you that how good is your approximation, right? How good is your guess. So this is the point I wanted to make about the part. So that basically tells you all the subtleties you need to know about these kind of problems. Now, what is remaining is, so this is basically everything. Now, what changes is complexity of the problem, okay? The amount of information, how complicated the problem is. So let's do another example, which is actually a historic example, is the ground state of helium atom. So that is where the surface Z parameter will come. Everything is clear so far, right? So this is all the machineries you need to apply. You need to know the grounds, you need to estimate the ground state energy. You need to see if you can improve that, and you have to estimate the overlap between that with the actual ground state, and that you can do without actually knowing anything. Without actually knowing
Sir,
anything.
can you explain that term of selection of that excited state? Means that
Sorry?
excited state term means plus 9E not that term.
Yes.
How this is coming means.
Yeah, can you explain? Can you try?
This is 0 not mod square E not. This is ground state term and plus some.
So what should be there? So first one is ground state. The second one could be the first state and second state and third state,
Yes.
like that. Right? So now I'm
Yes.
throwing away all the states. I'm just keeping one state.
Okay.
Okay. Now why should I put 1 minus 0 0 tilde?
In that ground state is already counted in that.
Yes.
So I am taking out that.
Yeah. So if I estimate all the other states as that, so it will be always this energy, this guy will be always greater than this guy, right?
Yes, but
So all I'm trying
why
to
not
prove is the
4? Why not
yeah,
4 E not means?
you could have chosen 4 also. It's just a
Okay.
choice.
Okay. Okay.
But the point is, at the end, what you are trying to prove is not what is this, right? You are trying to prove that this is greater than this. You are trying to prove a bound.
Okay.
Okay. Now there
Okay.
is another reason why I am not choosing. No, I said it wrong. Why did I say that? Can you guess? Why am I not choosing 4? It's not that you can choose 4. You cannot choose 4.
Cost terms. Cost terms means.
Parity.
Hmm.
It's a matter of parity. You want to put the same parity terms. Okay.
Okay.
If you take a product of odd even function, it will vanish the average, right? Because it will be overall odd. You see?
Mm-hmm.
Okay. Okay. Now what we'll do? We'll do a helium atom. So we are trying to prove a bound. We are just trying to prove it is better than that. We are not trying to actually estimate it, because we cannot actually estimate it unless you know accurately the E naught and ground state. Okay. I hope it is clear to everyone. The inequality and why am I choosing from the first excited state I am choosing is n equal to 3, not n equal to 2. Okay, so we will try to do now helium atom. Helium atom ground state. I'll set up the problem and leave for now. So Z is equal to 2 now. So no longer Z equal to 1. And we know that that if I think of this problem as two independent hydrogen atom, right, or two independent electron, instead of thinking any link, any correlation between them. So if I try to think it as two independent electron, then the energy of each one will be minus Z square with some factor in correct unit. This is actually Rydberg unit, so minus 4 Rydberg. So this will be the energy, and then the total energy will be just for the first one and second one, and this will give minus 8 Rydberg, and this is nothing but minus 108.8 electron volt, okay, which is almost like 30% or 35% off from the experimental value, which is minus 78.98. Okay. So now what to do? So we have clearly ignored many things. First of all, if there are two electrons somewhere here or somewhere in other orbit, let's say just two electrons, they should have some Coulomb interaction. Okay. So one factor is Coulomb interaction. Second factor is screening. Screening is something you have probably done in classical electrodynamics. It simply means if I have a positive charge and so there is one electron and then another electron, then what one electron will see is screened by the other electron. Okay? It is like saying if I am here, even if I am in the same orbit, the other electron have screened some of the charge of this electron. Have you learned this effect in electrodynamics or somewhere else in atomic physics? Is there anybody who doesn't know about this effect? Screening
We
effect?
learn that in chemistry for the PDF
Okay.
orbital.
Okay, that's good enough. Okay, so I want to take into account of these two effects and see how close I can go. So we will apply both variational principle and perturbation theory. Okay. So this is where I'll stop, and you can play with this problem a bit. You take a wave function psi r1 r2, ignore the spin of the electron for the time being. Later we'll also bring that in. We may not do that in the class, but you can bring that in. Write down this wave function without spin and try to calculate using perturbation theory the energy correction due to Coulomb effect. So this will be this psi 0, psi 0. So calculate just the first order correction due to this term. So put this wave function e square r1 minus r2. So try to calculate this term, and that is where we will start it off. And then we will add the effect of screening variational. So first we will do perturbation theory, then we will apply variational approach, and we will see how close we can go to the actual solution. Okay. Yeah, so that's roughly all for today. Is there any question? So if you have internalized the hydrogen atom and the particle in a box problem, then everything else is just a matter of complexity. There is conceptually nothing new in this variational principle chapter. Okay, very good. So we'll see you next week. We'll finish the variational chapter, and then hopefully I will need half a class, and then we'll move on to WKB. And then hopefully next week itself we can start on the time dependent perturbation theory. That will be a long chapter. Sorry? Yeah.